And so the next group is called Synchronous Drones. I will let the presenters introduce themselves.
Hi, I'm Saleh Al-Madan.
I'm John Emhoff.
And I'm Adam Dubs.
So our project today is Synchronous Drone. For the introduction, unmanned aerial vehicle are a category of aircraft that fly without a pilot, and drones can be remotely piloted or controlled or programmed to fly on their own. Remotely piloted vehicles must establish ground communication all the time. UAV or drones have a wide range of applications and are currently work, for example, military application, weather forecast, filmmaking, aerial photography, and making delivery, among others. For aim of our project is developing a system that would enable two drones working together. The two drones taking off simultaneously lifting an object that would be otherwise be too heavy for one drone. For the object of our project, the main aim of for this project is to design and simulate and construct multi-drones system which will be able to drones fly together. For the design, controller unit process all the information. The drones are fitted with communication modules to both receive and transmit signal to and from the ground station. The controller unit steers the drones based on the information received from the software. For the specific, the make of the drones used in this project is CoDrone. The drone comes with an image flow sensor, accelerator, gyrometer, and IR sensor. This eliminates complexities in implementation of the code. The CoDrone works just on the Arduino or Python code, but we use the Python code. So for the project simulation, we have simulated the project using Simulink. However, the Simulink does not support the CoDrone because the CoDrone just uses the Arduino or Python code, while the Simulink will only export the C programming.
So originally we were going to use two of the drones built by a previous senior design group's project. However, these drones were used for another purpose, so we ended up having to buy our own drones. The drones we decided to go with in the end was the Robolink CoDrone Pro, and we bought two of them. So here are some of the advantages and disadvantages of this particular model of drone. So the good things, and the main reason we chose these drones, is because they come with Robolink's software, which can be used to easily program them to fly in a specific pattern. Additionally, these drones were relatively inexpensive compared to most of the similar alternatives that perform similarly. As far as the bad things, the issues with these drones are that they're very small in size and as a result are not able to lift very much weight. However, they can still be used to demonstrate the concepts of our project. The other issue was that the battery life we discovered was very short. They could only last about 8 minutes of continuous flight before they needed to be recharged. To help alleviate this issue, we had to buy spare batteries so that they could be interchanged during testing. And finally, these drones do not support the Mavlink protocol, which is the protocol used by many drones to allow them to be controlled by a lot of open source software such as ArduPilot or Drone Code. Because of the fact that they did not support this, we were basically limited to the proprietary Robolink software that they came with. So here is a simplified example of how the synchronous flight algorithm works. Initially, one drone is chosen to be the so-called leader, and the rest are considered to be followers. This leader drone can be programmed to fly according to a given pattern to perform a given task, and you can do that using any normal flight controller. Then, in real time, the position of this leader drone is relayed to the computer running the Synchronous Drones software. That drone's position is then offset to create the desired formation of the drone suited to the user's application, such as, in our case, lifting an object which might be too heavy for only a single drone to lift by itself. And finally, the follower drone or drones are each flown using a flight controller separate, which is set to maintain this newfound position. So for the software, originally we wanted to use Simulink in order to generate the code for the flight controller, since that's what we designed it in. However, we found that Simulink can only generate code in C or C++, and the Robolink software is only in Python or Arduino. As I previously mentioned, since the drones don't support Mavlink, we had to use the Robolink CoDrone library in order to program the drones in Python. Some of the functions in this library did not really work how we wanted them to for our purposes of flying multiple drones at once. So we ended up having to write a lot of the code for the flight controller ourselves. And the drones use an IR sensor to detect their height and movement during flight and to make corrections. Their IR sensors were not accurate enough for our purposes, but we were able to improve their accuracy by quite a bit by applying a filter to them.
So we had to program the flight controller for a single drone first. And just a shout out to MATLAB. I watched a lot of their video tutorials on namely these three, but others as well to help understand these concepts because beforehand I didn't really know. So the flight controller code, basically, we had it set up so that the yaw, the throttle, the pitch, and the roll would have separate PID controllers. So there would be 4 PID controllers in total. And in the actual Python code, we had 2 Python classes, the PID and the horizontal PID. And I'll explain the difference between those two later on. And then we had 2 methods for handling position conversion, the convert to absolute location and the convert to relative location. And then in the main method, there's a basic state machine to control target destinations. So the class PID, initially we used this class for all of the controls, but as we developed more, we separated them out. It was mostly used for throttle. And showing from left to right is changing the parameters for those classes to get a better rise time. And the IR sensor was pretty accurate compared to some of the other sensors. And then we had the clamp value of 95. And the max value that the CoDrone for the throttle could have was 100, and the minimum was negative 100. So 95 was just a little bit beneath that. So for the X, Y position control, we had the horizontal PID. It's similar to the previous class PID, except there's extra code and methods added to turn off, turn on, and reset the integral value. That way, if you had a larger distance to traverse for the drone horizontally, you wouldn't have the issue of continuing to increase the integral and causing a massive overshoot. So it would turn off when the target changed, but it would turn back on when it got close to the target. And the optical flow sensor was unreliable. There were times it would work perfectly and give accurate readings, but there is a lot of other times where it would change. And so we tried various methods to try and improve the accuracy and more important, the consistency. So I tried different floor surfaces, like I laid my blankets out on the floor. This was the initial setup. The blankets didn't work, so I tried large checkered patterns and smaller checkered patterns on the floor because the XY position is determined using the optical flow sensor. It helped improve. It still had a lot of trouble with it. So tuning the PID controllers was pretty difficult. And then the drone frame of reference. The measured location is dependent on the drone's yaw. So if you have the absolute frame of reference here, if the drone turned, then you'd have the drone frame of reference, and what you would get fed back to the controller through the sensors would be based upon the drone's frame of reference, not the absolute. So you have to convert it to figure out where you actually are. So I had these two methods to do that. And the basic conversion calculations that we had determined were these set of equations from the measured to the real, and then from the real to the measured. So we'd have to use the measured to the real to get the sensor information and figure out where the drone actually is. And then from the real to the measured, we'd have to do so that we could set the target destination for the drone. And I initially tested it, the equations in Excel to make sure they would work. So if you had random yaw, like a bunch of yaw changes, you could get a measure position that looks like this graph on the right, but the real position that the drone's moving in could be a circle. So you could get very different results. So the horizontal control setting, here's an example of one of the runs. I was trying to control it so that it'd be able to move, move in a square with a side of 305 millimeters. And here's the image flow data. This here, this tail here is from taking off, and this tail here is from landing, because it will bounce, and you can see it in the height graph here, and it would flip over every once in a while. But as you can see, the goal was to go from 0 to negative 305 to negative 305, 305 to this corner, and then back to 0, 0. And the image flow sensor wasn't reading that. Like, it wasn't the same as what was outputted. So the image flow sensor was having trouble. And then data comparison for like the absolute versus the image flow. This is another run. Same goal, still having troubles. So the final position for the X, for instance, was 9. for the relative what it was measured as, but after doing the absolute conversion, it was 78. So slightly different, but either way, the final actual position was -60 when measured out physically. So the image flow sensor was giving issues. Sometimes it would work perfectly, but not all the time. For the synchronous drone design, it was basically we would use input control variables from the first drone, the leader drone, and we would take the height from the leader drone, and we would use a PID controller to control the difference between the height of drone 1 and height of drone 2, and we would subtract that value from the throttle from drone 0 to control the throttle for drone 1. And here's an example of it working for the height sensor. Now, this is for the height specifically. I only did it because the other sensors, I wasn't able to get the PID tuned enough so that it would work properly. But for the IR sensor, because that one was pretty good, I worked on that. So here's the first one, and a problem here was the drone leader was a drone I did most of the testing on. So by the end, it needed a throttle of about 30 in order to stay level, whereas the newer drone would need a throttle of about 0 to stay level. So there is quite a difference. So this was one of the initial tests, and you could see as soon as it got negative, it bounced back up. Here, it followed it more closely, but one of the things I added to this was I had it so that once it reached the target destination, it would no longer work in synchronous. It would work asynchronous. So as soon as it reached the goal of 1 meter, then both drone 1 and drone 2 would go back to their respective controllers with the target value of 1 meter. But here it never reached close enough, so drone 1 followed drone 0. But here it did reach, so drone 1 stays at 1 meter, and drone 0, because it was having issues, would slowly decline a bit. So here's a quick example of the height working. Show it again. It's just the rise time. So on the right, you have the drone that's following its own controller, and then on the left, you have the drone that's the follower. So the left is the follower. And then specifications met. Overall, the project was about 55 to 60% complete. The tasks that were accomplished was we had the height, throttle, and yaw controller tuned. We had the XY position controllers coded, but not tuned correctly. We had the relative to absolute positions calculated, and then the synchronous height controller was coded and semi-tuned. The tasks remaining are solving the XY position problem with sensors to get it better controlled, and then applying the synchronous height controller process to both roll and pitch for the second drone. Our sponsor was Dr. Gupta, our advisor was Dr. Tanner, and a special thanks to Miss Persley for her help buying the second drone. Any questions?
Yes, this is Karun Gupta here. Can you hear me?
Yes, I can.
Yes.
All right. Thank you very much for making this possible and bringing this through this remote media, which we are, of course, all tuned to now. My questions are as follows. Number one, the height seems like, or Z parameter was not part of PID control at all.
So for 1 minute. This here. The Z parameter is the height. So you have input of the drone height for the first drone, the leader drone, and then the height of the drone for the second was put into this PID controller, and then that value was subtracted from the throttle of the first one. Does that answer your question? Or?
Sure. Just a follow-up on that. So the two drones have to be flying at the same height to make them synchronized?
Yes. For the IR sensor is a little bit more absolute. So they don't have to be the same height, but if they were starting off on a different height, so for instance, you had one on a table, one on the floor, they would be they would, yeah, there would be the difference of the height between their starting positions.
Sure. But for the stable state, they have to be on the same height.
Once it reaches a stable state, yes, they're supposed to be at the same height. And I switched it, I had it in the code so that it would switch from, once it reached the target, at least for the height, for the horizontal, it would be slightly different, I would imagine, but for the height, yeah, they're supposed to be the same height once they reach the stable position, but I had it so that it switched from synchronous once it reached the target to asynchronous.
Okay. How about the XY separation between the two drones flying?
The XY position, I wasn't able to get for the synchronous because I wasn't able to get it completely controlled for the individual flight controller. But it would work with the same principle, where it would take the X, like you would change it so that you'd have, if you're trying to control for the Y, you'd have the Y position for drone 1 here, Y position for drone 0 here, and then in the Y case, it would be the pitch. That would be the input.
Okay, one last question. Did I hear it right? That CoDrone, the two drones were from CoDrone, but their software Robolink is the only way to program?
Could you repeat the question?
My question is, the two drones were from the vendor CoDrone, if I understand correct.
Correct.
And the software, the control software, was to be written in their own provided platform or programming environment, which is Robolink.
Yes, they have a library of functions you can use for Robolink. But you had the option of using either the Arduino controller or Python for coding. The Arduino one we didn't use because you could only connect the Arduino controller with one drone at a time, so you couldn't make it synchronous. So we went with Python so that we could connect it directly to the computer.
And so what was the role of the computer? Was it just the programming, or was it for some real-time control applications or aspects were also controlled by the computer?
So you'd have two Bluetooth modules connected to the computer, and the computer would take real-time information, program the drones. So if the drones got disconnected with the computer, the drones would stop functioning.
Okay, thank you.
Dr. Tanner here. The method that you had of disconnecting the PI controller until you got close is really quite clever. Did you have it kick in at first and then take it out and then put it back in, or did you just keep it out until you got a particular distance away?
So are you talking earlier on?
The horizontal PID.
Okay, so yeah, we had it so that it would be set so that for instance, for the X controller, the roll, it would, if the target destination is different from destination by at least some threshold, say like 50 millimeters, then the integral would turn off and it would reset, and it would be controlled by the KP constant. But then once the roll, or once the X position got close enough within absolute value of 50 millimeters plus or minus to the target destination, then the integral would kick back in.
Have you done any looking to see if there was anything written about using that technique? Because it really is quite clever.
No, I had thought it up because I was running into, when trying to tune, I'd run into issues. As soon as I'd add the integral, it would end up shooting past and into my kitchen. So
right. Right. And as I said, your solution is a very clever solution. What you may want to do is do just a little bit of research on that, see what else has been done, and take just this portion of it and write a paper. I think it is a unique enough solution that you may be able to get a publication out of it.
Okay, thank you.
Okay, well, we have run out of time, and we need to get prepared for the next group. So in about 3 minutes, I need to turn the recording off.
All right, thank you. I think that, again, very good job.
Good job, guys.
Thank you.